112 kilometers per hour, and 350 horsepower right under the seat. Engineers designed the GMC Astro for heavy hauling, but this layout turned every single run into a brutal endurance test. Sitting inside the flat, vertical cab meant positioning the human body directly over a massive Detroit diesel V6 or V8 block. Zero acoustic isolation. The relentless roar of the cylinders penetrates the thin floorboards, filling the confined aluminum space with a deafening sound pressure comparable to standing inside an active factory stamping plant. Heat from the running engine radiates straight upward, soaking into the seats and turning the tight interior into an industrial oven during long summer routes. The driver operates suspended directly above the rushing pavement. At maximum highway speeds, every crack and imperfection of the asphalt travels up through the heavy-duty leaf spring suspension, transferring aggressive kinetic energy straight into the steering column and the driver's spine. To maximize cargo volume within strict legal length limits, designers compress the entire mechanical heart of the tractor into the smallest possible footprint. The Astro utilized lightweight aluminum body panels to reduce the overall tear weight, but this thin metal shell offered absolutely no protective barrier against the mechanical noise. Managing the multi-speed manual transmission required constant physical exertion, forcing operators to perfectly synchronize heavy gears while enduring the unyielding vibration of the massive diesel block beneath them. The severe physiological toll of this direct, unfiltered connection to the road eventually outweighed the logistical benefits of a shorter wheelbase. Exhausted by the extreme noise and relentless heat, drivers rejected the cabover format entirely, causing the model to lose significant market share to conventional long-nosed trucks that finally moved the engine out of the cabin. The GMC Astro was merely one symptom. During the 1970s, American highways swarmed with machines that manufacturers celebrated as the ultimate pinnacle of engineering. Drivers experienced pure punishment. Why did trucks engineered to dominate the logistics market earn a reputation as the worst vehicles in transport history? Total ergonomic blindness. Corporate engineers focused strictly on profit margins. They saw maximized cargo space and theoretical fuel efficiency. The reality was different. Truckers battled endless mechanical failures, flawed structural designs, and hostile vibrating cabins. The gap between perfect paper specifications and a grueling 10-hour shift was massive. Now, we tear apart the original blueprints to expose the exact mechanical flaws that brought these highway giants down. The 1970s brought strict trailer length limits. The engineering answer was the Mack cruise liner, a towering flat metal facade planted squarely on top of a 12-liter block. Space meant money. Federal laws capped total highway train length. Every inch given to the cab reduced payload. Engineers made a ruthless choice. They pushed the driver all the way forward. They shoved the massive engine underneath. The cabover layout solved the legal problem. Packaging dictated the extreme physics. A giant inline six-cylinder Mack engine sits below, 11 to 12 liters of displacement, stuffed into an incredibly tight steel envelope. Scale this down, it equals packing a ship engine into a closet. The gap between cylinder head and seat vanished. It became a matter of mere millimeters. The driver essentially straddles the active block. This compact layout generates raw pulling power. It delivers between 250 and 350 horsepower. The heavy iron block pulls loads without hesitation. But the physics punish the operator. The process is brutal. You hit a steep mountain grade. Heavy payload forces maximum sustained throttle. The engine demands massive amounts of fuel. Combustion temperatures spike. Thermal energy radiates straight upward. It breaches the thin metal floor panels. The cab bakes. Vibration amplifies the intense sensory overload. The 12-liter block shakes violently under heavy load. The multi-speed manual transmission churns directly below. Gears grind loudly. You shift manually through a rigid linkage. The floor trembles with every single mechanical engagement. The boxy cab acts like a giant acoustic drum. The engine roar traps the driver inside. Then comes the unforgiving road surface. Heavy-duty leaf springs carry the rear-wheel drive chassis. Thick steel plates stack tightly together. They prioritize maximum payload capacity over human spines. The truck strikes a highway expansion joint. The rigid steel springs barely compress. The shockwave hits. It moves rapidly through the solid frame rails. It passes straight through the hard seat mounts. It slams directly into the driver. Zero mechanical isolation. Zero physical mercy. A standard 10-hour shift becomes pure physical torture. The constant aggressive heat transfer never stops. The loud mechanical noise deafens the ear. Saving space for cargo stripped away all basic comfort. The direct engine placement guaranteed chronic driver fatigue. Drivers absolutely hated the exhausting layout. The extreme physical toll outweighed the hauling benefits. Yet the machine never stopped pulling. Top speed was completely secondary. The ultimate goal was consistent pulling power on endless inclines, dragging heavy freight uphill at a steady 96 kilometers per hour. To remove heat and vibration from the cab, engineers moved the engine forward. Under the massive hood of the GMC General, they hid 12 liters of displacement and 318 horsepower. This was a return to classic geometry. A heavy steel nose extended far ahead of the driver. The cab was finally quiet. Steel firewalls physically separated the block from the workspace, ending the era of sitting directly on a vibrating furnace. Thick chrome details and sharp, squared-off metal lines defined the towering facade. Deep within the frame sat a Detroit diesel V8. Heavy drive shafts channeled torque into a 13-speed manual gearbox. Every gear shift demanded precise physical effort. A standard 6x4 wheel configuration kept the chassis planted on the asphalt. Rigid leaf springs absorbed the harsh impacts of imperfect highways. The machine pulled heavy freight at a steady 120 kilometers per hour. The physical scale was imposing. The hood stretched out like the bow of a cargo ship. Dual exhaust stacks delivered a deep, percussive rumble that shook the floorboards. It was pure mechanical intimidation, but sheer mass did not guarantee market dominance. Despite the vast interior space, the roaring engine, and the blinding chrome, the General remained trapped in the shadows of its rivals. The industry was already shifting. Brute force and perfectly square steel facades had exhausted their potential. Drivers refused to settle for rigid boxes, opening the door for a radical change in shape. Engineers attempted to correct past mistakes by radically altering body geometry to reduce aerodynamic drag. In the late 1980s, the Peterbilt 372 appeared, a heavy tractor completely devoid of sharp angles. A standard truck stop back then was a fortress of square steel, filled with massive flat grills and towering chrome stacks. Against this rigid backdrop, the new model presented a seamless aerodynamic silhouette. The smooth, contoured surface of the cab sliced the oncoming airflow, eliminating the heavy turbulence generated by classic flat-faced designs. It resembled a high-speed rail car far more than a conventional heavy hauler. The visual contrast was absolute. Beneath this controversial curved shell sat an inline 6-cylinder diesel engine. The power plant delivered over 400 horsepower to the rear wheels, providing enough torque to maintain a steady cruising speed of 120 kilometers per hour. Engineers compressed the transmission options into standard manual setups, focusing strictly on maximizing fuel efficiency over long highway stretches. The exterior form was dictated by pure aerodynamic logic. Highway wind glided silently over the sloped fiberglass roof instead of violently crashing into a wall of metal. The engineering was flawless, yet the market rejected it completely. Drivers who spent decades commanding aggressive steel hoods actively despised the soft, rounded cabin. The critical detail causing friction was the panoramic windshield, a massive, curved expanse of glass that distorted reflections and broke every rule of traditional truck aesthetics. Maintenance challenges and poor daily utility only amplified the alienation felt by operators. The Peterbilt 372 collapsed under its own radical vision, remembered entirely for its strange appearance rather than its actual highway capabilities. Pure mechanical roar. 15 liters. Floors vibrate. Peterbilt tested hoods. Freightliner engineers resisted. They tried to save the cabover layout itself through the Argosy model. Engines sit below. Detroit diesel and Cummins power plants. Iron cores heat. Temperatures spike instantly. Noise penetrates steel. A flat nose cuts headwind. No front hood. No buffer zone. 15-liter blocks scream beneath the seat. Physical discomfort dictates every highway mile. Every transmission shift rattles human bones. Engine vibrations travel up steering columns. Basic air suspension cushions structural impacts. It struggles against rigid steel frames. The 6x4 rear drive pushes hard. Heavy traction holds on steep grades. American truck drivers hated this geometry. They demanded conventional chassis space. They refused engine-mounted driver seats. Domestic sales plummeted almost instantly. Cab-over maintenance totally failed mechanics. Heavy cabs tilted completely forward. Routine repairs wasted valuable terminal hours. Why did Argosy maintain positions in other markets? Strict international laws intervened. Foreign highways cap road train sizes. Europe and Australia heavily penalize length. Every structural inch costs cargo capacity. Flat structural fronts save trailer space. Fleet managers prioritized absolute transport efficiency. Corporate operators ignored daily driver comfort. The Argosy survived across the ocean. It dominated tight industrial port terminals. It hauled heavy timber on trails. It pulled dusty Australian outback trailers. Corporate profit margins completely destroyed ergonomics. Harsh commercial survival demanded extreme compromises. The compact aerodynamic frame squeezed maximum utility out of restricted international space, relying entirely on brutal mechanical pulling force that peaked at a crushing limit of 600 horsepower. In 1996, the Kenworth T2000 hit the highways, an attempt to merge traditional 600 horsepower muscle with futuristic aerodynamics. Beneath the hood, 15-liter Cummins and Caterpillar inline-6 engines delivered massive torque, pushing fully loaded trailers to a cruising speed of 120 kilometers per hour. At this velocity, the physical behavior of the machine completely changed. The flat, imposing chrome grille was gone. Instead, the oncoming wind hits the sloped nose. The high-pressure airstream glides up the steeply curved windshield without separation. It wraps around the rounded roof and streams seamlessly past the integrated side skirts. This continuous aerodynamic flow eliminated turbulence zones, drastically reducing drag and cutting fuel consumption over thousands of highway miles. Large transport companies immediately recognized the mathematical advantage. Corporate fleet buyers ordered the tractor in massive quantities, filling cross-country routes with thousands of these slick aerodynamic domes. The sensory experience also shifted. Pneumatic air cushions beneath the 6x4 chassis absorbed the harsh highway joints, isolating the heavy steel frame. A 40-ton load hitched to the rear glided effortlessly over rough asphalt. The manual and automated transmission simply faded into the background, operating quietly behind the smooth ride. Yet, this corporate pursuit of efficiency ignited a rebellion among independent truckers. The sleek, egg-like silhouette stripped away the classic squared-off identity of the American road. Drivers accustomed to viewing a massive, angular hood found the steep drop-off disorienting. Furthermore, the complex, curved body panels proved difficult and expensive to replace after minor impacts. This sharp conflict between corporate fuel savings and deeply rooted driver preferences forced the manufacturer to adapt. Assembly lines eventually phased out the aerodynamic pioneer, replacing the model with subsequent versions that brought back the familiar, aggressive angles of the past. The trend of smoothing corners reached its peak in the Peterbilt 587 model, which forever lost its massive chrome nose. For decades, American highways belonged to brutal metal giants. Square hoods, massive grills, vertical exhausts. That era ended abruptly. Corporate ledgers demanded absolute efficiency. Every drop of diesel mattered more than loyalty. Engineers placed fuel savings above historic tradition. Wind tunnel tests completely erased the aggressive angles. Flowing curves replaced flat panels. The prominent chrome front end vanished into a heavily enclosed, rounded fascia. The classic identity was gone. Underneath the sculpted fiberglass exterior, the hardware reflected this corporate mandate. The truck utilized the 12 9/10 liter PACCAR MX inline 6-cylinder engine. Output ranged from 380 to 485 horsepower. Fleet managers loved the data. A 6x4 rear-wheel drive setup pushed the chassis down the interstate. Advanced air suspension absorbed the harsh impacts of broken asphalt. The ride quality matched a luxury passenger car rather than a heavy hauler, but this mechanical progress came with a sensory cost. Old-school highway tractors used to roar. Raw mechanical vibration was an integral part of the driving experience. This new model eliminated that entirely. Thick sound insulation wrapped the cabin like a sealed vacuum chamber. This acoustic barrier completely swallowed the familiar deep rumble of the older diesel engines. The interior became a quiet, highly ergonomic workspace. It isolated the driver from the controlled explosions happening just a few feet away. Total sensory deprivation. Logistics corporations bought these units by the thousands. The aerodynamic shape drastically slashed fuel consumption on long runs. However, independent owner-operators firmly rejected the machine. They saw a generic fleet vehicle completely stripped of its mechanical soul. The pursuit of perfect aerodynamics had wiped out the brand's recognizable identity. Sales figures eventually plummeted once factories fulfilled the major fleet contracts. The massive assembly lines permanently stopped producing the model. It quietly vanished from the official catalogs, fading out without any fanfare. Design yields to utility. A 9-liter diesel and 260 horsepower pull loads daily through heavy city traffic. The transmission engages, allowing the driver to seamlessly drop a gear while maneuvering a loaded trailer across a congested metropolitan intersection. Engineers designed the International TranStar 8600 specifically to infiltrate dense commercial zones and dock at narrow urban warehouses. The entire mechanical layout prioritizes constant stop-and-go efficiency over unbridled highway speeds. Under the sloping hood rests an inline 6-cylinder diesel engine featuring displacement scaling from 9 to 13 liters. The mechanical acoustic signature is remarkably controlled. At idle, the engine produces a muffled and steady rhythm, completely eliminating the aggressive rumble traditionally expected from American heavy transport. Generating between 260 and 350 horsepower, this powertrain might appear critically underpowered for steep mountain grades. However, when measured against the strict parameters of regional transport, that exact output perfectly satisfies the fundamental requirements of continuous urban logistics. Torque channels down to the pavement through a dedicated rear-wheel drive architecture, while reinforced suspension arrays stabilize the chassis under constantly shifting commercial payloads. Inside the cabin, designers discarded driver luxury entirely, installing rigid, easily cleanable surfaces suited strictly for brief operational shifts. Zero emotional attachment. Corporate fleets purchased the model in massive volumes to sustain local supply chains, yet the operators behind the wheel rarely developed any brand loyalty. The International TranStar 8600 survives in industry logs strictly as an industrial tool, moving regional freight for decades without generating a genuine historical legacy. Attempts to artificially combine brands for long routes created deep technical conflicts. In the 1980s, Volvo and General Motors launched a joint project. Two schools collided. A shift began. The Volvo White GMC Heavy project emerged. Europe brought strict precision aerodynamics. Smooth exterior panels replaced raw flat steel. Integrated cabs drastically reduced overall wind resistance. Wind tunnel data dictated front angles. The aerodynamic shape sliced the highway air. Consumption dropped immediately. This was a structural departure. America brought force. A heavy Detroit diesel block sat underneath. It held 12 liters of displacement. That internal volume equals 12 compact sedan engines. The inline 6-cylinder powerhouse vibrated continuously underneath. It generated from 300 to 400 horsepower. Two distinct philosophies operated together. Mating these two systems proved highly complex. Engineers paired raw power with manual transmissions. Drivers physically shifted through 10 or 13 gears. This gearbox allowed exact torque control. Heavy freight moved across steep mountain passes. Power flowed directly to the rear 6x4 drive. Air suspensions absorbed massive road impacts. Metric components met imperial hardware constantly. Visual contrast deeply shocked the traditional trucking market. Conservative operators despised the sloped hood. They aggressively demanded classic chrome details. They wanted flat-nosed truck styling. The engine sounded noticeably quiet. Corporate fleets noticed. Streamlined cabs saved serious cash. Form fought function. The venture struggled with parts integration. Replacing broken components became a logistical nightmare. Maintenance shops lacked specialized hybrid mechanical tools. Supply chains suffered from dual identity. The machine remained a relentless regional workhorse. The setup guaranteed steady forward momentum. This controversial platform successfully maintained a cruising speed from 112 to 120 kilometers per hour. But real market disasters occurred when introducing raw aggregates. The 13-liter max-force engine was supposed to deliver 475 horsepower. It stood as the mechanical heart of the International ProStar. This was a bold aerodynamic flagship featuring a sloped front, engineered specifically to slice through the air and slash fuel consumption. The powertrain relied on a standard 6x4 drive layout. It promised steady highway performance. Inside the shell, designers minimized acoustic intrusion to create a basic, quiet workspace. That was the initial corporate pitch. History took a different turn. The reality completely shattered those blueprints. International chose a highly controversial engineering path to meet strict federal emission mandates. Instead of adopting the industry-standard liquid urea injection, they built an aggressive advanced exhaust gas recirculation network. The engine forced massive volumes of hot, dirty exhaust gas directly back into the internal cylinders. The system choked on its own soot. Carbon buildup heavily clogged the intake valves. EGR coolers fractured under intense thermal stress. Boiling coolant leaked into the main combustion chambers. The mechanical failure cascaded across the country. Check engine lights illuminated by the thousands. Engine power dropped instantly. Dealership lots quickly overflowed with paralyzed machines. Endless lines of aerodynamic trucks sat permanently parked against chain-link fences. The familiar highway diesel rumble faded into the dead, metallic silence of grounded fleets, waiting months for replacement parts. Repair bays remained backed up for weeks. A single cracked cooler meant days of lost cargo movement. Logistics operators rapidly bled cash. One stalled ProStar cost a transportation company up to $800 a day in pure downtime. Defects in just one auxiliary emissions network completely eradicated the economic advantages of a highly capable flagship. The illusion of fuel efficiency vanished behind catastrophic repair bills. The manufacturer eventually faced billions of dollars in warranty claims and massive class action lawsuits. Frustrated logistics providers refused to tolerate the chronic unreliability. Fleet directors signed the necessary corporate paperwork, initiating the mass dispatch of thousands of barely used tractors straight to long-term technical maintenance facilities. Hours of downtime due to defective systems forged a harsh market rule. Innovation fails. Raw power dies. Aerodynamics cannot fix broken valves. Design promises collapse. The highway demands durability. Road behavior beats specifications. Engineering reliability dictates survival. A supply chain spanning 3,000 miles stops. Dead fleets bankrupt. Millions vanish instantly. Logistics empires bleed cash. The asphalt exposes every hidden structural flaw. They promised to revolutionize freight. Instead, they became warnings. These ambitious models secured their permanent place in heavy logistics history strictly by teaching engineers exactly how not to build a commercial tractor.